Hello and welcome to Module 6. In this module we'll be learning about ecosystem boundaries, photosynthesis and respiration, trophic levels, food chains, food webs, ecosystem productivity, energy transfer efficiency, and trophic pyramids. So we'll be coming back to this checklist here to make sure that we've covered everything. First of all, what is an ecosystem? Well, an ecosystem is a natural unit that has non-living and living organisms in a given area. So the non-living and living part of that is important to distinguish. So some of the non-living things that are important would be like the water, the soil, the atmosphere, and the living could be the animals, plants, microorganisms. Most ecosystems, it's hard to determine where one ecosystem stops and the next begins. They interact with each other immensely. However, sometimes it is easy to distinguish, such as when you enter a body of water from the land or you go into a cave. But in other cases, the ecosystems can have a transition area as you leave one into the next. And that transition area, there can be an overlap of biotic and abiotic components, such as the vegetation, etc. Here's a picture of two different ecosystems. What I'd like for you to notice on this one, this is Yellowstone National Park, one of our most beautiful national parks. Larger than that boundary is the national forest boundary, and then even larger here is the ecosystem boundary. So you can see that the boundary can be quite large, and then in the next picture over, you've got a much smaller ecosystem, obviously. It's just a small puddle in a rain-filled tree hole, but it has quite a diversity of microbes and aquatic insects. I'd like to take this opportunity to really tell you how important I think the photos and captions are. Many students, as they're reading a textbook, they'll skip over those photos and the captions, but I think that they are immensely important. On the next page here, there's the word biosphere. It's one of my favorite words. It's really, really important. It's on your list for your reading guide, and I won't be going over all of your vocabulary, but for this word, I wanted to make sure that I pointed it out. The biosphere is a region of our planet where life resides. It's about a 12-mile thick layer around the Earth. It includes the deepest ocean bottom and the highest mountain peak. All right, photosynthesis and respiration. Hopefully you know these equations or they are familiar to you already. It's important that you know the inputs and the outputs. So what's going into photosynthesis and what is coming back out. So what's going in would be solar energy, water, and carbon dioxide. And then what's coming out would be glucose and oxygen. And notice that these two equations are very similar, but the arrow has been reversed. So respiration is the opposite. It's also important that you recognize that all organisms perform respiration, even plants, and that's something we'll be learning about in the lab in class. Later, we'll talk about the role of photosynthesis and respiration in the biogeochemical cycles, especially the carbon cycle. So you can see that carbon goes through both of these processes. Okay, next page. This is a picture of a food chain and just the food chain. So you notice that the grasses are eaten by the zebra, which is eaten by the lion. One thing, this is not new to you, you've seen food chains for years and years, but one thing that's important to notice is the direction that the arrow points. So sometimes students want to put an arrow from the zebra to what he eats, but it's really important that you recognize that the energy in this, in a food chain goes from the thing that is providing the energy to the thing that it's being eaten from. So is the direction of the energy. Okay, this is much more realistic. Obviously, this is a food web, and a food web is simply many different food chains all combined. So this is what a real situation could look like in an ecosystem. All right, moving on to productivity of ecosystems, GPP and NPP, they're so important. So the gross primary productivity and the net primary productivity. Here's the equation. Net primary productivity equals the gross primary productivity minus the respiration by producers. The gross primary productivity is the measure of the total amount of solar energy that the producers in the system capture and over a certain amount of, capture via photosynthesis over any given amount of time. So this is really important that we understand this and we can compare them. So let's look at this picture again. This is gross and net primary productivity. So you can see the gross primary productivity coming in and the net. So what happens is producers will typically capture only about 1% of the available energy. So here's the rest of the available energy that is not being captured by the producers. This is called the gross primary productivity. Then about 60% of the GPP is typically used for respiration. So that means the remaining 40% of GPP is used for the growth and reproduction of the producers. This part is known as the net primary productivity, or the NPP. So here we go, 40% of GPP supports the growth and reproduction of the plant itself, and then 60% of that is lost due to respiration. Okay, let's do a little math example here. So a forest has a net primary productivity of 1.4 kilograms of carbon per square meter per year, and the rate of cellular respiration is 2.4 kilograms of carbon per square meter per year. So what is the GPP? Well, remember we have the equation right here. Net primary productivity equals gross primary productivity minus respiration by producers. So I'm going to turn that into an equation really quickly here. NPP equals GPP minus respiration. Okay, pretty easy. So our NPP is 1.4, which equals GPP minus, and our respiration rate was 2.4. So GPP must be 1.4 plus 2.4, right? Because we're going to add 2.4 to both sides. And that would equal 3.8 kilograms of carbon per meter squared per year. So I hope that you see that's really simple. You will be seeing this again. Okay. Here's a picture that's really important. This chart shows that some ecosystems are much more productive than others. So you can see the tropical rainforest, very productive compared to like the tundra or the desert scrub. And you can kind of logic out why that might be just based on the environment and what kind of plants and weather they had there. All right, moving over here to trophic pyramids. So trophic pyramids are really interesting. I kind of broke it up into 3 different pyramids. So the number of organisms, here's a picture of a trophic pyramid. This shows the energy available to the grasses, which is 10,000 joules. Then the energy that is moved up to the zebra, and then the next up to the secondary consumer, which is the lion. Notice that only about 10% of the energy moves up at each given trophic level. So here are 3 different trophic pyramids. This shows the number of organisms. So the number of plants at the bottom is going to be much larger than the number of bunnies, and then the number of foxes, and then the number of wolves that eat the foxes. Wolves eat foxes? I'm not sure actually. Anyway, you get the point. The number of organisms at each level is going to decrease significantly. Also the biomass, so the living tissue. The plant matter at the very bottom is going to be much, much, much higher than the tertiary consumer's body mass. So this guy's body mass is much, much smaller than the plants, the grasses at the very bottom. And then what this one is actually talking about is this here. It's the energy. So the large amount of energy at the bottom, only about 10% of that is going to go up. The other 10% will, or the other 90% will be either lost or used during respiration, and metabolism. So 10% of that energy is going to go from the 10,000 joules to 1,000 to the zebra, and only 10% again up to the secondary consumers, the lion. Really, this number is more like 5 to 20%, but we kind of round out and make it about 10. So here's another example of a question that you might see. Here's a chart. So you see a trophic pyramid here, and a chart here. So the grass, this is between trophic levels. So from grass to rabbits, rabbits to foxes, and foxes to hawks. And this is the percentage of energy efficiency. So this time we're not assuming it's 10%. I'm giving you a specific energy efficiency. And I would like for you to calculate the energy in kilocalories that moves from the next to the next trophic level. So we start with 100,000 kilocalories, and we're going to go from 100,000 to 12% efficiency. So you probably don't need a calculator for this, but just, I'm sorry. So 12% of 100,000 is 12,000. And so to round that out, we really don't need to round it for this case, but we've got 12,000 kilocalories. Now we're going to multiply that by 14% efficiency, and that's going to give us 1,680. So I'm going to call that about 1,700 kilocalories. And then we're going to multiply that by 8% efficiency, which will give us 134.4. So we'll say, I don't know, 130 kilocalories. So this is another example of a question that you might see again. You're asked to calculate the energy efficiency in a given area. All right, that looks like the end. Let's go back to our first chart. Did we talk about ecosystem boundaries? We did. Photosynthesis and respiration, we feel great about that. Trophic levels, food chains, food webs, got it. Ecosystem productivity, we talked about that quite a bit. And energy transfer and trophic pyramids, got it. Hope you enjoyed Module 6.